Hello everyone, and welcome to today's fascinating journey into the world of quantum computing and parallel universes. I'm your host, and I'll be guiding you through the concepts and ideas that will challenge our understanding of reality. So, let's dive into Theorem 1, which states that the successful operation of quantum computers necessitates the existence of parallel universes. Definition 1.1. Quantum computer. To start, we need to define what a quantum computer is. A quantum computer is a device that uses quantum mechanical phenomena, such as superposition and entanglement, to perform operations on data. In this case, we're considering a quantum computer with n physical qubits. But what does that mean? Imagine a classical computer that uses bits to store information, but instead, a quantum computer uses qubits that can exist in multiple states simultaneously. Definition 1.2. Computational limit. Now, let's talk about the computational limit of our universe. The holographic principle states that the information content of a region is encoded on its surface. This limits the maximum information processing capacity of the universe. In other words, there's a fundamental limit to how much computation can be performed in our observable universe. But what happens when we exceed this limit? Axiom 1.3. Quantum interference. Quantum interference is a fundamental aspect of quantum mechanics. It allows quantum computers to perform operations that are exponentially faster than classical computers. However, this interference requires physical interaction between quantum amplitude components. Think of it like a symphony orchestra, where each musician plays a different note, but together, they create a beautiful harmony. Lemma 1.4. Interference patterns. In quantum algorithms, interference patterns emerge from the interaction of exponentially many amplitude terms. This is what allows quantum computers to solve certain problems much faster than classical computers. For example, Shor's algorithm can factor large numbers exponentially faster than any known classical algorithm. Lemma 1.5. Google Willow. Google's quantum computer, Willow, has demonstrated computational tasks that require interference between an enormous number of quantum amplitude components. This is a key example of how quantum computers can perform operations that are beyond the capabilities of classical computers. But what does this mean for our understanding of reality? Theorem 1. Main result. Now, let's put it all together. Quantum interference requires a physical substrate, but the number of interfering components in quantum computations far exceeds the resources available in our observable universe. This leads us to the conclusion that multiple universes are necessary to provide the required substrate. But what does this mean for our understanding of reality? Corollary 1.6. Many worlds interpretation. The many worlds interpretation of quantum mechanics provides a natural explanation for the success of quantum computers. It suggests that every time a quantum event occurs, the universe splits into multiple branches, each corresponding to a different outcome. This idea challenges our classical understanding of reality and raises questions about the nature of existence. Corollary 1.7. Experimental evidence. Finally, each successful quantum computation provides experimental evidence for the structure of the multiverse, supporting the idea that parallel universes exist. This idea is not just theoretical, it's supported by experimental evidence from quantum computations. Conclusion. In conclusion, the successful operation of quantum computers necessitates the existence of parallel universes. This idea is supported by the many worlds interpretation of quantum mechanics and experimental evidence from quantum computations. As we continue to explore the mysteries of quantum mechanics, we may uncover even more surprising insights into the nature of reality. Thank you for joining me on this journey, and I hope you've enjoyed this exploration of parallel universes and quantum computing.